Today, the topic of discussion is NASA's Deep Space Network, DSN. Before that, let us understand the space communication between spacecraft and Earth. The space communication between spacecraft and Earth stations is a complex process that involves several steps and technologies. Here's an overview. Spacecraft transmission. 1. Data generation. Spacecraft instruments generate data, which is processed and formatted for transmission. 2. Modulation. Data is modulated onto a carrier wave using techniques like phase modulation or amplitude modulation. 3. Frequency selection. Spacecraft select a suitable frequency band for transmission, considering factors like signal strength, noise, and interference. 4. Antenna. Spacecraft use antennas to transmit radio signals towards Earth. Normally, such communication develops a delayed radio communication. It refers to a situation where there is a noticeable time lag between when a radio signal is transmitted and when it is received at the intended destination. The factors which causes the delayed communication are mainly due to 1. Distance. The farther the spacecraft is from Earth, the longer it takes for signals to travel between the two. Some examples. International Space Station is 250 to 260 miles, 400 to 420 km. Hubble Space Telescope, 340 to 350 miles, 540 to 560 km. Moon, 239,000 miles, 384,000 kilometers, average distance. Mars Curiosity rover, 140 to 250 million miles, 225-401 million kilometers. Voyager 1, 14.2 billion miles, 22.8 billion kilometers. Voyager 2, 12.1 billion miles, 19.5 billion kilometers. New Horizons, 4.1 billion miles, 6.6 billion kilometers. Cassini-Huygens, 890-1000 million miles, 1430-1610 million kilometers, before the orbiting. 2. Signal speed. Radio signals travel at the speed of light, approximately 186,000 miles per second, but even at this speed, signals can take several minutes to hours to reach Earth from distant spacecraft. 3. Orbit and position asterisk. The position of the spacecraft and Earth in their orbits can also affect communication delay. For example, when a spacecraft is on the opposite side of the Sun from Earth, communication is delayed due to the Sun's interference. American Space Agency NASA established such a robust communication network called the Deep Space Network, DSN. The Deep Space Network, DSN, is a network of large antennas and communication facilities that enable communication between Earth and spacecraft that are exploring our solar system and beyond. History. The DSN was established in 1958, with the first antenna built at Goldstone, California. Since then, the network has expanded to include additional locations in Spain and Australia. The DSN is operated by NASA's Jet Propulsion Laboratory, JPL, and consists of three main locations around the world. 1. Goldstone Deep Space Communications Complex in California, USA. 2. Madrid Deep Space Communication Complex in Spain. 3. Canberra Deep Space Communication Complex in Australia. Key features. Large antennas. Each location has multiple large antennas, ranging from 34 to 230 feet, 10 to 70 meters, in diameter. Transceivers. The antennas are connected to transceivers, which transmit and receive radio signals. Signal processing systems. The received signals are processed using sophisticated signal processing systems. Capabilities. 1. Deep space communication. The DSN enables communication with spacecraft that are millions of miles away from Earth. 2. High gain antennas. The large antennas provide high gain capabilities, allowing for sensitive signal detection and transmission. 3. Multiple frequency bands. The DSN operates on multiple frequency bands, including S-band, X-band, and Ka-band. 4. Redundancy and backup. The DSN has redundant systems and backup facilities to ensure continuous operation and minimize downtime. Supported missions. The DSN supports a wide range of NASA and international spacecraft missions, including 1. Voyager 1 and 2. 2. Mars Curiosity rover. 3. Cassini-Huygens mission. 4. New Horizons. 5. International Space Station. There are some fun facts about DSN. 1. Distance record. The DSN has communicated with spacecraft as far away as 13.5 billion miles, 21.7 billion kilometers. 2. Signal strength. The DSN can detect signals as weak as 1/100th the power of a typical cell phone signal. 3. Asterisk 24/7 operations. The DSN operates 24 hours a day, 7 days a week, to support continuous communication with spacecraft. NASA's Deep Space Network, DSN, is a powerful tool for communicating with spacecraft across the solar system. Here are some of its advanced capabilities. 1. High data rate communication. DSN supports high data rate communication, enabling spacecraft to transmit large amounts of data, such as images and scientific measurements. 2. Low noise amplification. DSN's low noise amplifiers enable the detection of extremely weak signals from distant spacecraft. 3. Precision tracking. DSN's precision tracking capabilities allow for accurate determination of spacecraft position, velocity, and trajectory. 4. Spacecraft navigation. DSN provides navigation support to spacecraft, enabling them to adjust their trajectory and maintain accurate positioning. The future of NASA's Deep Space Network, DSN, is exciting and challenging. Here are some potential developments and advancements. Upgrades and modernization. 1. Next generation Deep Space Network. NASA plans to upgrade the DSN with new technologies, such as advanced antennas, receivers, and transmitters. 2. High power transmitters. More powerful transmitters will enable faster data transfer rates and support for more advanced spacecraft missions. 3. Advanced signal processing. Improved signal processing algorithms and techniques will enhance the DSN's ability to detect and decode weak signals. Emerging technologies to add up the DSN capabilities. Some like 1. Optical communication. NASA is exploring the use of laser communication systems for deep space communication, which could offer faster data transfer rates and lower power consumption. 2. Quantum communication. Researchers are investigating the application of quantum mechanics to secure communication, which could provide unbreakable encryption for deep space missions. 3. Artificial intelligence and machine learning. AI and milliliter can be applied to optimize DSN operations, predict and prevent system failures, and improve signal processing. Some challenges and opportunities ahead of DSN. 1. Spectrum management. The increasing demand for radio frequency spectrum will require careful management to ensure that the DSN can operate effectively. 2. Cybersecurity. As the DSN becomes more interconnected, cybersecurity will become a growing concern to protect against potential threats. 3. International cooperation. Collaboration with international space agencies and organizations will be essential for advancing deep space communication capabilities and supporting global space exploration efforts.